RAG is Retrieval Augmented Generation, and this is literally a game changer. One of the biggest problem, a very major blocker which stops it to be used in mission critical applications as well as core medical purposes, that they hallucinate. I've been working in AI for over a decade. This session, this particular 1 hour, it's gonna give you a very deep dive in terms of your understanding of how these models work and how we can make them even better. Today, I'll be walking you through the fundamentals of large language model and AI tools. And I'll tell you very openly that none of this is something which a non-technical or let's say a non-AI person or someone who's AI person, this is something which both the kind of scenarios can cover what large language models are and how they work under the hood. And you all can become a very refined, very powerful AI engineer. Number one is chain of thought. Let's say you push the model to think step by step, predict the next word or token in a sequence. It's important to know trained on huge amount of text, and the goal and the objective is to predict the next word or token in a sequence. That is it. So I'm going to begin with a quick introduction at mind and who am I, what I'm doing here. So it's important for you guys to know a little bit of background about me. Um, First of all, thank you for joining this webinar. My name is Aditya, founder of Create Bytes, CBX. I've been working in AI for over a decade with published research in human body, repositioning, and personalization. I've collaborated with India's defense sector, plus a lot of global conglomerates with Create Bytes. And I'm also the founder of yugyog.ai and Alteryx Labs. And if you guys want to know more about these products, you guys should just go to the web platform, get an idea about it. Today, I'll be walking you through the fundamentals of large language models and AI tools. And I'm excited to share practical insights and answer your questions along the way. So let's kick off with a quick poll, and you can raise your hand or drop a chat message, whatever is feasible right now for us, that if you ever used GPT or Claude or any other large language model. Would love to see if, let's say, you guys have used it. So you can just raise your hand. Okay, so Aradhya has used it, Govind has used it. Okay. Uh, uh, so camera is on. Camera is on. Yeah. Okay. So Khushi has used it. Okay. So I can see a lot of people who have already used the large language model. Uh, so whether you've experimented a bit or are just curious about it. Okay, this session, this particular 1 hour, it's gonna give you a very deep dive in terms of your understanding of how these models work and how we can make them even better in terms of their outcome and impact. Okay, this basic understanding can evolve you in terms of building a more impactful product, or let's say drive you towards a direction of a deeper understanding of large language model. So we'll just quickly jump on to a high level agenda at this point of time. So like our roadmap today, we are going to cover and we'll start with what large language models are and how they work under the hood, touching on tokenization, transformer architecture, and training objectives. How do you train and fine tune? We'll also discuss key challenges that large language models face and the tools we have to address them. For example, prompt engineering, RAG, fine tuning. We'll also cover some cutting edge techniques in prompt engineering like chain of thought prompting, few shot learning, and model optimizations. And I'll tell you very openly that none of this is something which a non-technical or let's say a non-AI person or someone who's AI person, this is something which both the kind of scenarios can cover, because ultimately after 2017, what we have seen as a trend is that AI and usage of machine learning has just become simpler. So it's important to understand the concepts and you all can become a very refined, very powerful AI engineer. And again, to just at the end, we'll also touch a topic called as scaling trends. Throughout, I'll describe some slides which can guide you, and we are going to finish looking at the future trends and then what should be a call to action for, let's say, the next set of learning activities which we should be doing. And I'll be sharing some resources, open source GitHub link with you at the very end. So that's basically going to be our overall perspective. And like before we begin with what are large language models, how do they work and other things, the very simple thing which all of us know about and we have heard about it. Why prompt engineering, fine tuning, and RAG? Okay, this is very common. Okay, why do we really need that? Why do we need fine tuning? What is the purpose of this? If we have large language models, why do we need that? Why do we need RAG? And like, why do we need prompt engineering? So first of all, to understand it, and because that's why I've asked the first question, that whether you guys know about Chat GPT, Claude, because these are large language models, so we at least know about it. If we know about it, we should start first with what are the challenges of these large language models. Okay, so the most important part is that these are amazing and built in a very general purpose manner. And because of that, they have some pitfalls. Number one is the lack of domain specific knowledge. A general model might not know the latest niche facts or jargons. It knows only up to its training data cutoff, which could be outdated. Number two, the handling of data. They can struggle with extremely large data or context if not properly managed. And there are some technical terms. Sometimes they misunderstand new acronyms or names since they haven't seen them enough. One of the biggest problem, and we have heard a lot of news, including the one which happened with Deloitte. This is a kind of a very, very major blocker which stops it to be used in mission critical applications as well as core medical purposes, that they hallucinate. The model may make up information that sounds plausible, but it is false. Let's say you state a citation, and once you state that, you come to know that this doesn't even exist. And this happens with these large language models. And then there are inconsistent results, another big problem. Running the same query multiple times can yield different answers. They sometimes miss obvious information present in the prompt or in the context. So, just one quick question. As I've mentioned about the changes, who all are here, and you can raise your hand, have experienced a model hallucinating or giving a wrong answer? Like anyone who has experienced that? Okay. Kushal, Manan, Aditya, Khushi, Madhav. Okay. A lot of you guys have experienced it. Yes. And you guys now are able to understand that if these are the challenges, there should have been done something for them. And that is why the topic is why prompt engineering, RAG, and fine tuning. Okay. Like also, if we basically look at this at a very high level, to address these issues which are present here, okay, engineers use tools like prompt engineering, RAG, fine tuning, and that's how you overcome. And not, I won't call it as complete resolution, but to a certain extent, you are able to understand what you need to do to at least get some acceptable outcome in some scenarios. And this brings up to our next slide, which is what is RAG? And how many of you have heard about this term RAG? Like you can raise your hand. Okay, Aradhya has heard about it. Oh, a lot of them. Ansh, Kushal, Dhruv, nice. Kripa. So you guys have heard about RAG. Okay, so like at a very high level, RAG is retrieval augmented generation. And this is literally a game changer. The slide explicitly explains a technique where we give the LLM access to an external data set or knowledge base. Okay, so like for example, you have a lot of scenarios where you would like explicit truth coming out. Okay, instead of only relying on its internal memory, the model can look up to facts from, let's say, documents or database or sometimes graph during the generation. But how does it work exactly? So typically, you set up a pipeline. When a question comes in, you first use a search or retrieval component to find the relevant documents from your overall data set. Then you combine these documents into the prompt or context for the LLM. The model then generates the answer based on the real data. I haven't touched the concept which basically enables it to do it, but at least you guys should know that what exactly and how exactly does it work. Now, as we have seen the challenges, what kind of challenge does it overcome? And that brings up the part of benefits. Okay, so the number one thing is it reduces the hallucination. I won't call it completely eliminates it, but it reduces the hallucination because answers are grounded in retrieved documents. It's less likely to just make something up if answers are coming from certain factual information present in the dataset. Better explainability. You can trace the answer back to the source text. It's easy to say the model got this from this section, this place. So you have an explainability of why did it come up with that answer. Number third, this also makes them up to date and also private for someone. Okay, even if large language models training data is old, RAG can use fresh documents which you have just uploaded and you can feed in your company's data. For example, let's say you feed in some legal judgments from 2024 to 2025. You can also put some medical records. So it's like you can keep it updated so that it just focuses on that. Okay, let's take one example that suppose we have a private manual for a machine. LLM didn't train on it, so it might hallucinate with that manual. But with RAG, we upload that manual and retrieve paragraphs. The model can then answer how to maintain, let's say, this machine for this activity. And using this manual text, the model can answer. Okay, so it's important to understand and differentiate LLMs, and then there is a challenge for LLM, and RAG to a certain extent is able to solve a particular aspect of LLM, which is a use case for a lot of people. Okay, now a question to all of you. Can anyone think of a situation where RAG is going to help? Okay, like you have got an idea. Let's see that if you guys are able to, and you guys just need to raise your hand if you can think of, okay, Nilesh can think of a situation where RAG can help. Nilesh must be thinking about Python or Django based scenario. Harsidak is also able to think. Kushal. So guys, you are able to think. But before I jump further, I can give another example. Just raise the hand, the person who, like people who are able to understand RAG at a very high level. I've not given any technical details so far. So you guys are able to. So Aradhya is able to, Dev is able to. Okay. Okay. So I see less hands. Does it mean that you guys are still not able to understand the concept or you are able to? Okay. 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 I can see more hands coming in. So you guys are ultimately able to understand at least basic level of functional side of what exactly is this RAG and what it does at a very high level. Okay. So let's jump on to the next important section. Okay. Again, one last example so that you guys are able to understand in a very, very deeper detail in terms of RAG. So assume that you have some new documents which have come up. You know for sure that these documents were not like LLM last version was, let's say 4th April 2025. You have your private data, and these documents have never been fed to LLM for training, and LLM is very general purpose. So what do? You just upload those documents in a RAG system and you build it. Okay, use the LLM for generation capability, and then it can actually produce an outcome with respect to those docs. So that is retrieval augmented generation for you in a very, very basic functional level scenario. And it covers up a particular challenge of LLM. But now we are going to jump towards the next challenge of large language models and how these challenges, which I just described, can also be taken care to a certain extent via a concept of prompt engineering. Again, very basic is the art of writing effective instructions for large language models. What you can see on the slide, like let's say I've instructions which are given to the models and I define them. Okay. Key idea is more precise and detailed prompts typically yield better outputs. That's it. Okay. What you need to do now when you're defining a prompt, you need to be precise. Instead of, let's say, you say, tell me about cats, you should say, write a 300-word article on health benefits of petting cats, suitable for general audience. Provide it the context. The more you describe the style, audience, or format, the better. For example, pretend you are a, let's say, you are a famous detective like Sherlock Holmes, writing a diary entry about a particular mystery. So that's how you provide a context. Text variations are also important. Small changes can have a big effect. You can try rephrasing or adding examples and you'll see the outcome changes. Also, review the final outputs. Always check that the answer for accuracy is coming out to a certain extent or not, and if required, tweak your prompt to a certain bit. The final outcome, as their general models, and we have seen the challenges, may not always be good enough. Okay, to give you an example, let's say I want to generate a product description. If I just want to generate a product description, I can, in a very lazy manner, can write describe this tool. On the contrary, I can also write in a very, very interesting format, write a compelling 50-word product description for an energy efficient drill targeted at home, do it yourself enthusiasts, highlighting its key features, key components, and how to use them. The second one actually is giving you an idea and clarity and tone to a certain extent, the audience and the length too. Okay, I'll give you one simple example, okay, which you can try on your own. Let's say explain quantum mechanics. You all must be having some access of large language models. You can just try it out. And then what you do, you refine it. And you say explain quantum mechanics for high school students in 3 paragraphs. And that's it. That's it. That's basically prompt engineering. And there's nothing on top of it. So this is important to understand that like there are ways in which you can handle LLMs to produce a better outcome. Now, if we just jump towards some strategies which people follow, and we should know the terminologies. Ideally, a lot of times you're following those, but if we know the terminology, we can actually think about strategies to improve it. You would have seen people give you a GitHub link. These are the best prompts which you can use to do this. Do you know you can also do the same? You can also generate your own prompts. You just need to know the right strategies. You just need to know how and what need to be done. And it's no rocket science. It's very straightforward, very simple. Number one is chain of thought. Let's say you push the model to think step by step. For example, instead of answer X prompt, let's think this through step by step. And this is something which I use a lot. Let's think this through step by step. The model then generate intermediate reasoning, often leading to better results on logic or math problems. Self-consistency strategy. Ask the model the same question several times, okay, and takes the most common answer which it brings. Now, this may not be true for a lot of subjective scenarios, but it is true for a lot of strategic and objective scenarios which can come up. Okay, this basically filters out all the random errors. To give you an example, I can tell that generate a graph for me from this document. Then I again ask the same question, generate a graph for me for this document, generate a graph, but like in different ways, in different manner. And then finally, I see what are the consistent things which are coming up, which basically is a very interesting way to figure out something. And I've used it for a very specific purpose. Then we have a concept of few shot prompting. And I'll tell you, you are already doing it, which is we already saw this in a very, let's say, basic scenario in the beginning, that the prompt is guiding the model. So you can tell the prompt to do this and then come up with the next prompt. Then, so these are few shot promptings. Okay. The chain of thought, and I want to focus on that. It's really powerful for math or multiple step reasoning. Okay, to give you an example, if I ask it to solve a particular problem, and also a lot of times you'll see for sequencing activities too, especially the scenarios where you have, let's say, some molecular activities involved, there also it works quite powerful. So you just say, and then even if you guys are coding and you are using cursor, you can follow the same thing. Add step by step, makes it right, let's say the logic around it, and then you go with x1 y1 y2 kind of outcome which can come for you. Okay, so that's where the difference come in. But let's jump on to the next big thing. And again, what I'm trying to give you an idea about, instead of going towards the direction of what are LLMs, you guys are already using it. So let's just directly jump towards what are the challenges. And at this point of time, to use them, what are the techniques which we are using, like RAG and prompt engineering and some advanced techniques, which basically help you evolve from that. But now we are going to jump towards a very interesting section, which is at this point of time, there are some key players which are in the market. And LLMs and AI is not just about the software of it. Okay, there are different foundational aspects which one should know about right now. And you guys know the kind of $1 trillion growth which Nvidia is doing. So it leads with specialized GPUs and chips for training and inferencing. And guys, you should look at an architecture which is groundbreaking breaking research, and they come up with B12 or B2 something servers, which is called as Blackwell architecture. H100 is on Hooper architecture, H1 100 and H200. Blackwell architecture is the new thing, which Nvidia has come up with, and it's very powerful. Then you have cloud platforms where, guys, you can even use API calls from these cloud vendors. They provided you platform as a service, whether Google has its Vertex AI, Microsoft Azure also has its platform as a service, and then Amazon also provide these. So you have foundational cloud models also, which provide you an access of large language models. The best place for me when I'm using it is Hugging Face. Hugging Face, it's basically huge in the data science and AI community. It gives you libraries and a lot of models that anyone can download and use. And again, even the existing LLMs, they provide you APIs. Okay, whether you take Anthropic Claude, you take OpenAI, you can call APIs. Okay, even let's say you can use them from a perspective of consumer side, where you're just prompting, like you use Perplexity, ChatGPT, and other chats. Okay, now the important part, let's say if you consider, is the way these systems are being used across the globe. So there are B2B companies which have been built on these foundational models, and you can build things on top of it. But if you know the basics about it, you can build much more powerful products with that. Okay, I've given you an idea about the AI hardware, the foundational model, but I've also given you an idea about like how companies can use it. I would like you to just raise your hand and tell me one thing. Have you guys seen any company which is using these LLMs? Okay. Any company which you can name of, just raise your hand that yes. One example is Midjourney, they're using. Okay. Pratik has seen it. Okay. Govind, Nilesh also has seen it. So what's happening? There are companies, Jaskaran has seen it, which are using these LLMs. But ultimately, what I want that someone from you basically is not just using them, but building the foundational models, like building the core research from that. Not just using it, but either you are participating on the hardware front or building the foundational cloud for these LLMs, or let's say have deployed some open source models. And that's where we can actually give our proof of uh, knowledge plus the overall authority in this domain. So far, most of these things are coming from like somewhere outside India. Would love to see if something comes up from any of you. It'll be interesting. Okay. But yeah, this is important. And also, I'm going to touch one more aspect towards it, which is basically the multi-modal and the new architectures which have come in. Again, the concept of mixture of experts. Uh, okay, raise your hand who have heard about DeepSeek. DeepSeek? Yes. Okay. A lot of you guys have just, yes. So the concept there is basically mixture of experts, but I'll just explain. So LLMs used to handle only text, but now we have multi-modal models. Okay, what exactly it is? For example, GPT-4o can take images as input along with the text. Vision language models like, let's say, Delhi combine text and image generation. So the new architectures, overall, the concept is like mixture of experts. These are models where different parts of the network specialize and only a subset gets activated for a given input. Again, I'll explain. Different parts of the network, that is the neural network, specialize and only a subset gets activated for a given input, allowing a huge model, let's say billions and trillions of parameter, but only using specific parts at a time. The concept makes the inferencing very efficient. Why it is important? LLMs by default are energy inefficient in terms of the kind of energy they consume. If they consume more energy, they'll have more cost. If they have more cost, they'll become less sustainable for general purpose use cases. But the architecture of mixture of experts, when you have only a certain parameters or let's say set of networks which can be used or should be used, it basically allows the model for producing faster inferencing and for the same outcome consuming lesser energy and so more efficient. So it's important for us to understand this. And then we have the other concept, which is agent models. Okay. I'll explain one concept to you, but before that, raise your hand who can, in a single line, differentiate between what is a workflow and what is an agent. You've heard about workflows. Okay. And then you've heard about, let's say, agents. Can anyone who can give an idea? What is the difference? Like, just raise your hand if you know the difference. Okay, Joylene can tell, Kripa can tell, Nilesh can also tell, Manan can tell. Okay, okay. So the simple thing is a workflow is a concept which is static and has been around for years now, decades now. It's like if you do this, the decision making there, if it goes in this direction it is this, if it goes in the other direction it does that. So it's a static path. So workflow is very path oriented, that what path one creates and then which direction one takes along the way to finally reach somewhere. But the idea is it's a path oriented scenario, it's very static and it's decision making based, like a logic rule driven engine. That is a workflow. But the concept of agent, it's goal oriented. It's like I want to achieve my final goal to send an email. It doesn't matter what path I take, what kind of dynamic evolution I do while doing that. But agents basically are, and a lot of agents are built on top of these large language models. But the concept is that they are goal driven. And it is important for us to understand that why exactly they're goal driven. So there are AIs that can perform tasks by interacting with tools or the overall environment, plus the concept of LLMs being taken from them. So it's like you interact with file management system while sending an email to upload a file, you do this and that. Okay, but ultimately they are trying to achieve a goal. Let's say there's an AI chatbot that can browse the web, run a Python code, call API autonomously, and then this makes them agents that can set goals and execute a dynamic multi-step process. And to achieve that goal, they can shift their path on their own and they self-evolve. All these trends, which are mixture of experts, agents, points to us in a direction, a future where models that do more than just chat. And it's important to understand that in the beginning, chat GPT is not just being used for chat. Okay. So like while it started there, they are like the trends which we see clearly show us that where the future is going. They can see, they can act, and they are specialized for doing some powerful dynamic activities. Okay, and I'll tell you the next steps also from here. While you have agents, you'll see a lot of, let's say, physical environment interaction happening with these AI systems at a commercial level, which is going to come up. Okay, so let's basically deep dive towards the direction of practical nature now, which is how do you set up an environment? Okay, so you have, let's say, like there are various environments, and I hope you guys have seen in mind like PyEnv is present. Then you have virtual environment wrapper, you have Conda. Uh, Raise your hand if you guys have used a Python environment before. Okay. Kripa, Aradhya, Deepansh. Okay, you guys have used a Python environment. Now, the interesting fact is that there are a lot of good ways and possible scenarios where your local environments may not be as powerful to use it, which is you use Google Colab. If you do not have, let's say, a local VS Code setup or some other IDE setup and using Python. Okay, if you're using that, you just need to create a virtual environment, install libraries like, let's say, you're using OpenAI, then you install Transformer, then you basically check your hardware, what GPU configuration you have, and other things. On the other hand, you can also just open Google Colab, and I recommend that in future when we'll be doing a lot of practical sessions too. Google Colab is something which we'll be using a lot, and all the open source code base of the projects and products which we'll be building, all those are going to be present through the Google Colab GitHub open source code base. So you can just copy paste your code to Google Colab and run it. The good thing is that, okay, raise your hand if you guys have heard about Google Colab so that I do not just skip that. Okay, Manan, Kushi, okay, you guys have seen Google Colab being used. Perfect, perfect, perfect. So again, just a small information, just type Google Colab on Google, enter, and then you can just write, let's say, you start using it. There'll be some installations which you always have to do, like transformer installation and all, but a lot of setup activities you do not need to do. Plus, it provides you TPU, GPU access to a certain extent, so it's very powerful. And if you are in college, Google Colab and there are other platforms which provide you free access of a lot of credits which you can leverage and use. Okay, finally, we are going to touch the topic, what are large language models. Okay, so far what we can understand is there are challenges with these GPT and all, and to overcome that, we've defined and refined some solutions which are like RAG systems, prompt engineering, some techniques like chain of thought which have come up. And then from there, we actually came to a scenario where we understood that the future or the progress happened with some better models, where you have mixture of expert concept and then agentic systems which have come up. But now finally we talk about exactly what are these LLMs. Very simply put, LLM is a huge, I won't call it like a large neural, but I'm going to call it huge neural network. Okay, it basically can have tens to hundreds to billions and now trillions of parameters trained on massive amount of text to predict the next word or token in a sequence. It's important to know, trained on a huge amount of text, and the goal and the objective is to predict the next word or token in a sequence. That is it. Predict the next token or word in a sequence. For example, given some text, the model guesses what comes next. That's it. Okay. It learns grammar, facts, reasoning patterns, and style from your training data. These models are auto-regressive and self-supervised. And again, I'll just give a quick brief. When I said auto-regressive and self-supervised, that means they learn from raw text without explicit labels. When you do a supervised learning, what do? Raise your hand if you know supervised learning. What are you doing with supervised learning? Okay, Manan knows about it, Nilesh knows about it, Kushi, Govind, Dhruv, you guys know about it. It's nothing but you are gonna annotate the data and say, with this is the data and this is how you train it, and then finally you check the answer. That is supervised. But these are auto-regressive and self-supervised, and again, simply put, they learn from raw text without explicit label. That means you do not need to do like huge amount of annotations which you have to do in supervised. Okay, imagine reading every book and article online. So you have some kind of power. Not sure if you guys have watched the series Gen 5, which has come up. And there's a girl who has a power to think in a very broad sense, and she can read a lot too. Okay, it's on Prime if you guys want to watch it. So imagine reading everything, like let's say books, articles online. You can start to predict what word should come next in any sentence. Okay, why? Because you've read so much, you know what is going to happen next from the old patterns, because your brain also work in a very similar direction. So that's essentially what a basic LLM does. The only thing is the scale is huge. You have trillions or billions of tokens. And the result is a general purpose text engine. That's it. So you've built something, and these LLMs are, again, the word we need to know is general purpose. And that's why, like, this word itself gives us the challenges which we discussed. Okay. Remember this thing that LLMs are powerful. They are statistical models, not all knowing in terms of what can happen, but also like logical thinking scenario. So to give a very basic example, you'll see that they have some scenario that they may not know about something, but because of the older pattern, they are predicting it. So we just need to know that these are statistical model because they are very pattern oriented with a next letter of word. Okay. Tell me one thing. When you have used in past any model, let's say GPT or Claude, you did not actually think about work but started interacting for fun. Who have done that? Like just for fun, when you first time experienced a model. Interesting. So you guys have, because I've also done that. That's why I was asking. So when you first time experience such a thing, it looks so powerful, so amazing that wow, this can do that. Okay, so you have someone who is interacting, but you need to know that behind the scene, it's not basically something which is like doing some kind of intuitive scenario, but it's just the pattern which it is following and showing you something. So next time when you think about it, think about it's very pattern oriented. So change the way when you look at or talk to a large language model. That is just figuring out the next word or predict the next letter in that word. Okay. Now, there comes the most powerful aspect. Okay, 2017 there was a paper, and I always talk about that attention is all you need. Raise your hand, and this I'm not who have read it, but who have not read it. Okay, attention is all you need. There's a research paper. It's a 2017 paper. Okay, Nilesh has not read it. Arpit has not read it. Govind has not read it. Okay, so one homework which I want all of you to do is just read this. Just search on Google 2017 attention is all you need. It's from Google. Very, very important, very interesting. And this changes the way you look at large language models. Maybe you'll not be, okay, research paper. How do you read a research paper? You start from the abstract, just read the abstract. Don't do anything, just read the abstract. Then just jump to the last section, which is the result section. Just go through that. That what it is able to achieve versus what it said in the abstract. And once you have done that, you skip the introduction because that contains a lot of literature review and all. You just jump onto the high level method. So you start from abstract, you go to the result, then you check the method. That's how you can read a paper. That's how I do it when I'm reading a research paper. It saves a lot of time. Okay. Again, okay. So the backbone of virtually all modern, okay, let's see how much time we have left. Okay, we have some time. Okay. So the backbone of virtually all models, which are like large language models, including the Chat GPT, Claude, and all, are transformer. This is like the core building block. There's a block diagram which you can see, which is like showing a diagram of a transformer layer. It has two parts: multi-head self-attention and feed-forward layers. Okay, I've just used some very idiotic words: multi-head self-attention, feed-forward, what it is. Okay, let's jump towards specific things. Self-attention. The model looks at the input token, words or subwords, and lets each token pay attention to other tokens. The cat is on the mat. Okay. So you take each word cat and check for how much of an attention the other words are giving to cat. So if you're talking about cat, it is on the mat. So mat is there, on is there, the is there. The may have less attention to it. So like then you first check for the, then for cat. So you recursively check for each word with respect to all the other words. So that's important to understand. That is self-attention. It does this multiple ways, which is to capture different aspects of context. For example, okay, take this as Sat and mat, which I just explained. Sat has a certain attention to mat, and then mat has a certain attention to sat. So the cat sat on the mat. The word cat will attend to sat and mat to understand context. Okay. Uh, let's take a simpler example here. Uh, when I say the cat sat on the mat, okay, I have the word cat. I want to see that this word cat, in terms of the attention, how much should I give it to mat? Because cat is on the mat, so mat has a bigger attention span. But at the same time, does the has that bigger attention? So you'll give attention some numbers, 0.5. So the mat has 0.7, for example. Similarly, when you go to sat, bigger attention is mat and cat, but not on and the. So it's like every word you look at the other words, then you give some corresponding attention numbers, which are like numerical weightages to this, and then assign it, and that becomes the attention. Able to follow? Raise your hand if you're able to follow, or I'll give another example to you. Okay. Okay. Deepansh, great. Okay. So again, it's important to know the word, and I'll explain it again because I see less number of hands. Okay. Model looks at the input tokens or words, and what it does, it lets each word pay attention to other words. Let each word cat, the cat is on the mat, cat, pay attention to the other word. Cat will pay attention to the, then cat will pay to mat, on, everything. Okay. It does this multiple ways, and that's why the word multi-head, to capture different aspects of the context. So the will pay attention to cat on the mat, cat will to the on the mat, then on to the cat mat. So it's like it does it multi-heads. Are you able to understand? Remember this, lets it pay attention to other words and does it multiple ways. Okay, now let's jump towards the next topic. Okay, and this example, there is a series which I've started on the Instagram, which is called as LLM on whiteboards. You'll be able to see a literal diagram of this example of the cat is on the mat, so on the whiteboard, so that you understand self-attention. But the reason I was taking a lot of time here is for you to know attention is a very important aspect. So when you're thinking of transformer, it's important to know that attention gives a kind of a detail which takes the transformer to complete its core objective. Now feed forward layers. After attention, each token passes through a simple neural network to transform this information. And then you will see a word again, feed forward layer. Simply each token passes through a simple neural network. And then the next important word is add and norm. What we are doing, we are adding residual connections and layer normalization, so the model trains more stably. Okay, again, whenever we use the word, just remember normalization. Okay, so that means you're talking about some kind of stable direction where we are going towards. So residual connections and layer normalization is one of the next steps. We'll get into these details in much more later sections. But right now, the idea is for you to at least know the words, understand some basics of it. We'll actually implement this, okay, at some point of time. But for the time being, just know the words. That feed forward layer is basically token passing through a simple neural network. Add a norm, crucially, we add residual connection and layer normalization, so the model trains more stably. These skip connections help the network remember the original signal. Very important to know. Okay, because what you have done, while the token is being passed through the neural network to do the transformation of information through forward layer, it's important that we do not lose the original signal, the original information, and add a norm take care of that for us. So very important part. And then you have very important concept, which is positional encoding, because attention itself doesn't know the order of tokens. The cat is on the mat, the is number one, cat is two. So this is the order of tokens. So attention doesn't know the order of tokens. So we add positional encodings to each token embedding so the model knows which word come first, second, etc. Important point. Okay, positional encoding. Again, I'll explain. So what is happening? You know about the attention, but you're not aware which is the order of for those words. So you pass on an interesting and a very simple concept that, okay, let's give them some order. And that ordering is basically nothing but positional encoding. So the order of tokens is then maintained, and you can see positional encoding going into the attention layer. You guys can see that? Raise your hand if you guys can see the diagram and see how the attention layer is capturing the positional encoding and input embedding. Nice, nice. Okay, perfect, perfect, perfect. So then we basically move on towards the direction of the important aspects now. You've got an idea about four basic concepts: self attention, feed forward layers, add and norm, positional encoding. At least you have not implemented, but you know the words to a certain extent. Okay, now let's do a little bit of deep dive into some direction of, let's say, how the overall functionality is working. It's important to know that. So transformer details in a more depth helps us know some important aspects in terms of the functional side, and we should know that to a high level. Okay, so we have already given an idea and understood an idea around, let's say, multi-head attention to a certain extent. But what it is doing, okay, and you can see the multi-head attention coming here. Okay, you guys can see that. Okay, it's important to understand that it allows the model to consider multiple interpretations of the context simultaneously. So multi-head attention is allowing the model to consider multiple interpretations of the context simultaneously. It's important. For example, one head might focus on sentence level meaning, another head on grammar, the other one on named entities, which are like metadata information. Having multiple head is like having multiple spotlights on different parts of the input. Now you understood the importance of multi-head. That what you're doing is one head focusing on the sentence level meaning, another one on the grammar, the other one on named entities. So multiple heads are having multiple spotlights on different parts of the input. Raise your hand if you're able to understand multi-head. Perfect. Ria, nice. Deepansh, Govind, Kushi, very good, guys. Nice. है ना? So that's the meaning of multi-head. Again, what you are doing, what is the intent of it? Multiple head and having it is like having multiple spotlights on different parts of the input. Then we have the feed forward network. This particular is a simple neural net applied to each token position. Okay, each token position you apply this simple neural net. What it does, it adds non-linearity and depth to the token. And we'll come to the to it later that why it is important. But ultimately, the feed forward network. Okay, you guys can see the feed forward network here, the block. Okay, what it is doing is it's basically giving non-linearity and depth, and it's a mathematical thing, but we'll come to that later on. Okay, and then the add and norm layer ensure gradients flow in a direction where we do not lose the original signal again. Okay, making the training, so it's, think of it as every time you're calling these, you're just passing the add and norm to it. Okay, for the time being, we'll get into the detail at when we'll go into the mathematics of it, but for the time being, just get this idea. Okay, now it's important that we understand that this is how it is working. So you have the input, and then you have input embedding, you have positional encoding, you have multi-head attention. All these things are working in parallel to produce a final output. So this at least gave you an idea of some terms of transformers. It's very easy, but at a very high level, what you should know is that you have an input, then you have input embeddings, then you have positional encoding, which you basically pass on. Then you have attention. Attention also multi-head attention. Why? Because sentence, grammar, other things can come up. And then you pass it to add and norm. And then you have a feed forward. Okay. Again, giving it, as we have discussed, like the depth and non-linearity. And then you basically pass it on to for the output embedding. So far, so good. Guys, raise your hand if you've got some terms, at least the naming of nomenclature of the terms. Kripa, Kushi, okay. Nice, nice, great. Pratik, Manan, okay. So we are going to move on to the overall objective of large language modeling. Core task is self-supervised, given a context, predict the next token. Simple objective, it can scale to trillions of tokens, leads to the emergence of complex abilities. Okay, objective forces the model to learn grammar, facts, reasoning pattern from data alone, making it powerful, general pre-trained. Okay, so that's basically the large modeling objective, which we'll get into the detail at a later stage, but you guys just should know how it works. But now comes a very powerful topic for us, and this is very important, and this is where you come to the basics. Again, we are going to cover all these in detail in each and every section moving forward, but this gives you an idea about the overall aspect, and you can see clearly how easy these concepts are. Okay, so before text enters the transformer, it should be broken into tokens. So what you can see is a concept where tokenization process, where you have raw text that gets converted to subwords, which gets converted to token IDs. To give you an example, here you've seen unbelievable. This can be split into unbelievable. Okay, this is basically called as byte pair encoding, BPE. What it does, it finds the common subwords. But the question is, like, you guys have heard about subwords, but why? Why is this subword important? Okay, anyone who has ever thought about, like, people are talking about subwords, I've heard about it, tokenization, but why? Raise your hand if you have ever thought of why. Okay, Nilesh has thought of why. What about the others? Manan, Kripa. Okay, so it's important for us. Aliza has also thought about why. Okay, why subwords important? It's a balance. If we use only the whole words, the vocabulary will be enormous. Okay, if we split into letters, sequences, it can get very long. Subwords give us a sweet spot. Okay, again, just check. Unbelievable. So they are giving us a very sweet spot in terms of understanding the mapping of IDs. So what you are doing with subword is just simplifying it. Okay, the whole concept is, can I simplify it so that I can use it for my mathematical operations in a better scalable direction? Very simply put. Okay, let's take a word, internationalization. Okay, you may split it into different subwords. Okay, just one quick question. How many of you guys think that internationalization can have two subwords or can have three subwords? Those who say three, raise your hand. Internationalization. Okay, Deepansh can think of, Dhruv can think of three. Okay, okay. What about two? That it is basically two. Okay, Pratik, Khushi, Kripa. So the concept is that simply understanding that how we can scale in terms of the subword. So why subword is also something which should come in your mind, that what exactly it is, why it is used. Once we have these token IDs, okay, try to understand. Each ID is turned into an embedding. Okay, what are these token IDs? Again, explaining it again. Subwords give us a scenario where you can see, let's say, unbelievable mapped to IDs like, let's say, 305, 1247, 329. So each subword piece has a numerical ID associated with it. And once you have these token IDs associated with it, okay, it basically is turned into embeddings. It's a vector with, let's say, n dimensions. and we'll discuss about dimensions too at in just the next slide. But you just understand. So the model works on these numeric embeddings and not raw text. It's important, even if they are language models, but actually behind the scene, it's all math. So what's happening here? Okay, so the concept is that you have a vector which is coming up. Now we are gonna talk about a very powerful, interesting concept, which is embeddings and positional coding. Okay, so guys, you can clearly differentiate now token IDs and embeddings. So what you're doing, first you do subvert, then you jump towards embeddings. Okay, so subvert tokenization is the concept and the word which is being used. And then once you have and then there are various techniques of subvert tokenization. One of them is byte pair encoding, which we have just seen. But okay, after tokenization, each token ID gets mapped to a dense vector embedding. Okay. For example, the cat sat on the mat. Each mapping to a different, let's take a dimension, 768 dimensional information. Okay. So these learned embedding capture the meaning of cat, which might be close in the vector space to a dog. And it is going to be, okay, what is a vector space? Okay, let's try to just understand. And this is again is going to be present in the Insta video too. You have heard about a Cartesian coordinate system. Cartesian coordinate system is a system where you can see X and Y. Okay, raise your hand who all know about Cartesian coordinate, where you have X axis and Y axis present. Khushi, Jakran, Deepansh. Okay, you guys understand Cartesian. Perfect. Oh, I can see a lot of hands being raised. So everyone understands. So X and Y we have. Now, think about it, the concept where you just convert it into a concept of meaning map. Okay, what is a meaning map? So what you do, you have a vector space where you keep similar meaning words together. Now, the similar meaning can actually be with respect to a context. Let's say smell, taste, look. Things can be similar color-wise, but they're very different. For example, you can have chili and you can have green leaves. Okay, and then you can have a green box. So color-wise, they are similar. So you have a dimension which compare color similarity in the meaning map, which is one dimension. Then you have another dimension which compare the taste. You have another dimension which compare the smell. So the meaning map can be a multi-dimensional, not just a 2D coordinate system, but a multi-dimensional system, which each dimension talking about a particular criteria on which you're going to decide the similarity. And then you define the vector. And the two vectors, if they're similar, their angle are closer, you're doing a vibe match. Can they do a vibe match together? So that's the meaning. Okay. So again, remember the fact that attention alone doesn't know word order. So what we do, we add positional encoding to each embedding. So while I'm defining the corresponding vector, it's important that we also define the order. And that is added with the help of positional encoding. What you can see, it's like a kind of like, if just take a look at the dimension and then the output 1, 2, 3, and then corresponding outcome here. And don't get into the detail, but I'll just give you one reference, a little bit of sneak peek. Okay. The encodings, which are like, there is a concept of rotary positional embedding. Okay. And these are basically sinusoidal positional code added to the token embeddings. Okay, there's a formula, but I've not given it here, but these are sinusoidal positional code, which is added. Okay, just for your, like, tomorrow if someone asks, these can be this and that. So this just, it basically depicts one example of it. Okay, now, so the input to each transformer block is token embedding plus positional encoding. The sum basically, so to give you an idea, this overall thing, which is like the overall sum of the positional encoding plus the corresponding token embedding, this goes through an attention and feed forward, which we just saw in this particular slide. Okay, where it happens. And all these building blocks are how large language models turn the raw text into, let's say, predictions, which are the next word or parameters present there. Okay. So again, positional encoding is an important aspect along with the embedding vectors, which basically move on and pass to the next level. Finally, let's jump towards the direction of the word which we use quite often, training and fine tuning. Let's try to understand. Training LLM is like a two-step or two-phase or two-stage journey. First is pre-training. What we do, we expose the model to enormous text, like let's say Wikipedia, books, everything, and train it to predict the next token. Okay. Let's say goal is to predict the next token in any sequence. I'm going to train it on a huge thing. What we do, we adjust millions or billions parameters so that model become good at the basic language task. Okay. So this is like very core of training. And at some point of time, I'll be putting a YouTube video to train a model from scratch, especially LLM. We'll do that. After the pre-training, we have a concept which is used quite often in B2B space and industry, which is fine tuning. What it means is taking the pre-trained model and training it further on specific data set or task. Example, let's say we fine tune on biomedical papers for, let's say, a medical chatbot system. We build that. Okay. Or QA pairs for a question answering bot. So what's our objective? The model is for a specific task. So we do a fine tuning. Example, OpenAI use additional data, let's say some kind of human feedback, which is reinforced learning from humans, and it ensure that GPT is able to follow instructions better. Okay. And that's what a lot of companies also do when they're using Llama. Llama is an open source model. Okay. And this is something which goes a little technical, but anyone who has ever tried fine tuning, not necessarily LLM, but any fine tuning, anyone ever tried it or read about it? Okay. Nilesh has tried fine tuning. Okay. Kripa, less number of people. But yeah, now you at least understand the core conceptual difference when we say training and fine tuning. Now, the important aspect, again, we are touching the terms today to just get the overall vibe and overall picture of this entire thing, which is basically the prediction process and context size. Once something is trained, LLMs generate text one token at a time. Important part, guys. One token at a time. Okay. So what's happening? What the model looks at the given context, outputs a probability for the next token, picks one, appends it, and then repeats. This is your core process. And over, we get a sequence of any length. This auto-regressive loop, and again, term auto-regressive loop is how the chat response or article generation happens when we are typing something and we're getting it. Okay, just understand behind the scene. Okay, the thing is, it outputs a probability for the next token. Number one, probability for the next token, then picks one of those and then appends it. Very simple. Probability outcome, picks that and appends it, and then just repeat over and over in a sequence. Now, very critical concept, and it had its own limitations, which basically causes a lot of B2B companies to pivot to figure out things, is the context window size. Raise your hand if you guys have heard about context window. Ever heard about the term context window? Govind, Nilesh, Deepansh, okay, Bhavish, okay, Keetan. So you guys have heard about the word context window. Okay, now understand the critical concept is the context window size. How many tokens the model can see at once? Like, let's say that we have GPT 3.5 Turbo, which can handle around 16,000 tokens. With GPT-4, I can handle 32,000 tokens. Okay. What does it mean? 16,000. So it means that how many tokens I can see at once in a single scenario. That's the context window size. So raise your hand who feel like if the context window size is less, it's better. Okay. Yes. So you are with me. So if raise your hand who feel like context window size is, if it is bigger, we have a better model. Okay, fine. That's good. So I can see that the hands are yes. So your ultimate target is to figure out a way to get better context size. So that's why if I have to use something where I have a lot of context which need to be given and the model need to know the full context of the entire thing, I would rather prefer to use GPT-4 as compared to 3.5 Turbo. Now, a larger context allows the model to handle larger documents, remember the older conversation, include more information in a single scenario. And for the same, practically Gemini was quite good because if I remember, I recall, and I think it gave in the very beginning 1 million token size and it became a big news. I don't remember that it was 1 million, but yeah, I think I remember it quite well. It's 1 million. So the kind of token length, context window size it got, it was huge. Okay. But understand every good thing has a limitation. Okay. So the thing is that it's important that longer context also directly means more computation. And that is why even after we know that longer context is good, LLMs have a limitation that they cannot provide like an infinite, let's say, context window. So self-attention. You guys, do you remember the transformer thing? The transformer thing which talked about self-attention scenario. Okay. Now, self-attention scales at O(n) square complexity. You guys understand complexity? Raise your hand if you understand the algorithmic complexity. We have used this a lot. Yes, Khushi understand, Govind understand, Jaskar understand. Okay, so all there is a concept which is called as algorithmic complexity. Okay, now the thing is that if you increase the context window size, there's a particular place called as self-attention. Think about it logically. If you have to give attention while given an outcome, and then that attention has to go through all different heads. If let's say you have one single, the cat is on the mat, but you have thousands of lines about the cat, then you and then that is all part of the single context window, the kind of complexity which is going to come. Okay, and then this is O(n) square. This limitation, it doubles the second the token increases, it doubles the computation and quadruples the overall computation. So it doubles up the kind of tokens, but like because we are talking about n square, it just quadruples the computation for us. Okay, it's important to know that difference. Okay, why and how it happens? It is because of O(n) square complexity. Now in 2021, and guys, you should look at that. These large language models are not using it, so I'm just giving you a sneak peek. In 2021, Stanford published a paper, and I'll share it in our like community link later on when we're gonna. You guys can just through your camera scan it and get inside the community. There's a paper which talks about S4 models, and if I'm not wrong, the term is state space control systems or something like that. They have built a system which works with a complexity of O(n). Okay, and they try to replace attention with a different concept to pass the positional data set. So you and then there's a model called as Mamba, which is quite powerful. So this is a way to overcome it, and it will take huge amount of time and billions of money, let's say amount of money for any big company to change their current foundational concepts, because you just cannot change it like this. So but there's a research going on to decrease it and the way it should be done. So just go and check for this 2021 S4 model concept, and I'll share the link to later on. Okay, now it's important that we understand the concept of scaling laws. Again, giving you terms so that you have an idea which thing is what. Scaling laws. It relate to model performance to size and data. Okay, size and data. So let's say we have n parameters. More model parameters generally mean the model can learn more complex patterns. So let's say you have billion parameter, you have million parameter, you have trillion parameter. So more model parameter simply means that model can learn more complex patterns. Data set, more training tokens helps in terms of the learning activities. Okay, now we have compute flops. And this compute flop is not something which is new, it is there for a while. more training, compute, longer training, bigger hardware, also results improve. Okay, so when I say that more training and from the hardware, it basically is like the concept which is called as flops, measurement of computational resources used. Okay, example from, let's say, if we just take some idea, let's say I have a 70 billion parameter and it was trained with 1.4 trillion tokens. According to the basic concept, what you're doing is you train for about 20 times the number of parameters in the token. Okay, so if you have 70 billion parameters, and this is not something which is hard fast, but you can think of it and start relating. You should basically compute these things in your mind. There is a parameter n, you have a data set d, you have flops. So if you have 70 billion parameter, okay, basically like what you do, you just multiply it with 20, and that is the kind of, let's say, data set which is 1.4 trillion tokens on which it is trained. That's how you can compute. And it is not something which is like hard fast, but there is a correlation with number of parameters, and for that number of parameter, how much of, let's say, training tokens you'll need, so that you can do a lot of benchmarking. It is very useful when you're trying to do some benchmarking for these things. Okay, now why does the bigger context matter? The model maintains more information during a conversation. It refers something that said, let's say, 100 turns ago, or let's say two chat back, this is what happened. So there are some important activities where you need better context. Okay, now let's jump on to the part where we just, okay, like you guys can look in the same model too, but you can also look in a concept which is like you can just follow it for Nemotron, Llama, and all too from the perspective of models. Again, we talked about prompts, which are instructions to AI models like, let's say, GPT-4, GPT-5 to generate human-like text. We have now understood the various ways to do that. And then you have role, instruction, 1, 2, 3 question. So like it is entirely and altogether different subject. But once you know the basics, okay, you can like evolve your own prompts. LLM changes, the prompt activity changes. Sometimes a lot of people prefer JSON information being used for prompts. So there are various ways to do that. But let's jump towards the direction of a concept, which is few shot learning. Okay, before I jump towards few shot learning, I want to know that how many of you have heard about few shot learning? Just raise your hand. Few shot learning. Govind has, okay. Hades, Kushal, Kushi, okay. Okay, so few shot learning, it means giving the model a couple of input output examples in the prompt so it learns the pattern. Okay, for example, describe the movie, example Titanic heart, Matrix, computer green, let's say Toy Story friendship. So example is that overall, what we are doing is we are showing the model a few questions and answer pairs, or some translation examples, so that model sees them and say, oh, this is the format, this is what I need to mimic. You got the idea? So how does it help? It explicitly teaches the model what we want without retraining it. It just adapts on the fly using the prompts. Got the idea? Let's say describe the movie The Lion King with these examples which are shown to you, XYZ, and let's say the model says circle, king, pride, something which is capturing the overall theme. The few shot helps because the model might need just one or two examples to generalize the activities and tasks. And that's why a lot of times in your prompt, you should give some examples. It can improve the accuracy. It can improve the scenario in which we have for a specific format for an output. But it's important that we choose good and right examples, guys. Now you understood the importance of few shot learning and how you should be doing it. Raise your hand if you are able to. Perfect, 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 perfect. Nice. Okay, guys. So we are gonna jump towards the scenario where, and we've already discussed the importance of context length. We have uh, already over 15 minutes, but I'll try to cover this up later on in terms of context length. But like there is an important aspect which one need to understand, which is optimizing the transformer for long context. Okay, and this is, we are going to skip the flash attention to and long net, which are the last two remaining topics, but we'll discuss these in later in detail. But I'm going to just jump towards this. Okay, and it's important that we understand to scale to a larger context. Let's say researchers like us, meaning you guys have to become good researchers. So yeah, so have like, let's say there's a concept which has come up, which is called as alibi positional encoding. It replaces the usual encoding with a linear bias that makes longer context easier to handle. Okay, so what you're trying to do, you're trying to figure out a way where I can handle longer context. And the word is ALIBI, alibi positional encoding. Okay, it helps models generalize to longer text than seen in training. Okay, so for example, there's a word called as sparse attention. Instead of every token attending to all the others, you remember cat set on the map, all the token need to attend to the others and then it has to go for all the words. Instead, it only attends to a particular subset. Okay, again, the word is sparse attention. This cuts completely from ON squares towards linearity. Then you have a concept of flash attention. This is a very highly optimized implementation of attention for GPUs. What it does, it reorders calculations to use GPU memory more efficiently, making attention layers faster and less memory hungry. Okay, again, we have read about sparse attention, heard about sparse attention, then we have flash attention. Highly optimized implementation around GPUs, which you use. What, and again, understand the core concept is it reorders calculation to use GPU memory more efficiently. That is it. That is flash attention. Then you have multi-query attention. Multi-query attention is MQA. Each head in multi-head attention has separate key and value. MQA shares those keys, and again, you remember multi-head attention? Okay, multi-head attention is nothing but like spotlight on different places. One spotlight on XYZ, meaning the other one on that, and that spotlight. One is on grammar, one is on sentence context. So each head in multi-head attention has separate key and value. MQA shares these keys values across the heads, reducing the memory usage. And this lets models use more heads without blowing memory. Okay, so this is the concept there. Okay, so flash attention, sparse attention, multi-query attention. Okay, I'm not gonna jump towards like the flash attention 2 or long net, but you guys are able to understand that you can optimize the transformer for larger context. You have alibi positional encoding, sparse attention, flash. Problem, the challenge was O(n) square and inference cost and time. Able to understand this, guys? Raise your hand if you can get an idea that there is a way to in which you can optimize. Jaskaran says yes, nice. Pratik says yes, Govind yes, perfect, guys. So let's jump towards the historical nature. Okay, and there are some interesting stories which basically come up with the historical nature of large language models. Okay, and before I jump towards the historical nature, I want to know from you how many of you have started using LLM in 2023? Okay, 2023. Okay, Manan, Jaskaran, battery is 10. Okay, Khushi, Nilesh, Pratik. Okay, what about 2024? Okay, 2025 started. Okay, so you guys have started 23, 24, 22 kind of a thing. Okay. So it's important for us to know the historical trend so that we know a lot of times history tells us where the future is going to be. Okay, so we just need to know how and what is happening in the history. Okay, 90s, 50s to 2016. Okay, like the models were at that time, like let's say very simple bag of words, like counting word frequencies. You have RNNs, LSTMs that processes text sequentially. LSTMs helped a bit with, let's say, context, but struggled with long sequencing. Okay, it's important to know what was happening at that time. 2017 and 18, and we need to understand 2017 18, transformer revolution happened. Two big leaps. Transformers, attention based, parallelizable. Okay, important. And then the other one is BERT. BERT was bi-directional, and it was very, very powerful in terms of understanding tasks. And then GPT starting the concept of generative trends, generative pre-trained transformers. Okay, important. So 17 18 was transformer revolution. You can just think of it in 50s to 16. See the amount of time and the speed which the evolution happened. Uh, and at that time, I also used to use RNNs, LSTMs, and the idea was text to be processed sequentially. No parallelization was involved. So it was ultra slow. And like it used to help a little bit in context, but the second there was any kind of, let's say, long sequencing and all, it just failed. 2019 to 22, we had the concept where you had scale and alignment. You have GPT-3, 175 billion parameter. It showed the kind of capabilities we can have by simply scaling it up. And then there were instruction tuning, reinforced learning from human feedback loop. Okay, that made models follow user instructions better. Okay, and we just touched this topic where OpenAI with an example where fine tuning happened, where reinforced learning from human feedback, which is RLHF. Okay, and Chat GPT was fine tuned with human feedback to be more helpful and safe. Okay, and this happened 1922, and then 23 25 we had the concept of multi-modality and future. Okay, again we discussed about mixture of experts. DeepSeek came this year. It's like December 26, 2024. DeepSeek came, so it just came, and then it just changed the way the optimizations can happen. So right now in this current scenario, we have the concept of multi-modal models, and we are trying to push the context windows, and then we are building agentic features. And you would have seen a lot of companies using agentic AI. So models are getting more reliable and integrated into the tools. So if you see, what you're going to see are the key milestones. Like we went from, let's say, a simple count based model back in 16 to neural nets to attention, and now at this time giant multi-modal agents. And this all happened in this very short duration from 16 to 25, just a decade. Okay, just a quick question for us. Like have you guys used Siri, Google Siri and all? Oh, I think okay. Yes. So my question to you all, have you guys used Siri or let's say any of these? It was back in 2010, 11, 12, 13. And now see the kind of models we have. You know, so there is a huge change which has happened. But yeah, with this, like you guys can comment here if you have anything to say. But yes, we are gonna close our session today, and I'll basically just give you an idea what we'll be doing in future, and what is next for us. So we'll be heading towards, let's say, in a direction where we'll go into some kind of research mode too, and we'll check about the future of context and agentic AIs in the coming side. Also, what we'll expect, and this is something which I will definitely touch upon because I've been doing a lot of research there. Like, how do you expect a longer memory? Let's say real time scenarios for a huge context. How can we have better and faster reasoning? Okay, you guys should always check for expanded models some kind of personalization models which are going to come up. These things will always help you know what's happening, and always go through some research papers. I talk about those in on either Insta or on YouTube. Check those too if you want to. Now, the important part, guys, are you all able to? I hope you're able to see the screenshot here. So it's basically the Insta channel. From there you guys can actually go and ask questions. Plus there's a GitHub repo link which will be shared with you, which will contain some of the code which I'm writing, and then we can also participate in some open source code activities once you've got an idea. So like overall we share quick AI tool tips, summarize notes from webinars, updates on the latest AI activities on Discord channel, plus also the GitHub repository where you can see LLMs and RAGs, and then whatever I'll be talking about in YouTube, there'll be a GitHub repository in which you can go and check. The important aspect is we will be covering a lot of future activities moving forward in terms of how and what you guys can do with LLM. And the whole idea and inspiration for me is you guys can make foundational models coming from India. Okay, but for that you guys need to know basics, and you guys are able to understand what you guys can do with future and build very powerful and interesting collaborative products. Okay, and we have been doing a lot of activities in Create Bytes. You can look at some of the products like yugyog.ai and Alteryx Labs. We have been building computer vision based products which involve human body anthropometric parameters. I've done my research on human body repositioning and personalization. There's an aspect associated with that. But doing a lot of things, guys should follow. If you have any questions, reach out to me on Insta. There's an email ID. You guys can just look at that email, reach out to the team, or otherwise I'll always be there on Discord where we'll be discussing new interesting stuff. But thanks a lot. Thank you everyone for joining in, and very, very nice connecting to you all. Thank you. Good day. Bye bye.